Howdy everyone. I had a wonderful day today and I hope you had a wonderful time too. Before we actually get back to the lecture, I want you to remember what we did couple of lectures back. It was a lab activity. It was pertaining to the concave mirror experiment. Please try to remember. The main purpose of that activity was to find the properties of images formed because of a concave mirror. Now we had a V stand, we had a mirror, the concave mirror, we had a scale for the measurement, and we used a candle, the flame of a candle as the object, and to catch the images we used a screen, a paper essentially, white paper. Now I'll try to remind you that particular activity, but before watching this entire video, I strongly recommend you to go back and observe that video once again. Observe the entire activity and try to remember that entire table that was finally drawn from our experiment. What we did in that experiment was we placed the V stand and the concave mirror assembly on the table. We arranged a scale and we moved the object, the candle, either towards or away from the mirror. Try to remember the result. Did we get the sharp image on the paper every time at the same location, or do you remember us moving the paper to find an appropriate location for the image? What we found out from the experiment was the image did not appear at the same location each time. That means for every object distance, there is a new image distance. So the image position will be different. That's the first conclusion. Another conclusion was regarding the size of that image. Was the image of same size for every object location, or was the size changing? And in fact, if you remember, for some of the results, we saw the image to be diminished. That means it was very small compared to the object size. And in some scenarios, the image was enlarged. That means it was larger than the object, larger than the candle flame. So that was about the image size. Now think about the direction in which the image is pointed. Of course, the object, the flame of the candle is always pointed upwards. But is it the same thing with the image? No, in fact. Try to remember how the image was formed on the screen and inside the mirror. Whenever we saw the image on the screen, it was always reverse. We call it, is it an erect image or an inverted image? Yes, the one on the screen, the paper was always inverted image, the reverse one. Whereas the ones that are formed inside the mirror, in one of the scenarios, we had to peep into the mirror and observe. So that particular case, we saw the image to be erect, similar to the object. Now that was about the orientation or the direction in which the image was pointed. Now our last scenario. We called some images as real and some as virtual. And the way we remembered it was any image that appears on the paper, the screen, we call them real images. And any image that appears inside the mirror, that means it does not appear on the screen but appears inside the mirror. We called that image as a virtual image. Now, these are all the things that we did for various distances of the object. Now that's all good, but what is the reason behind these results? Why is the image size changing? Why is the image location changing? Why is the image direction changing, either inverted or erect? And most importantly, why do we call an image as a real image if it appears on a screen, and why we call it virtual if it appears inside the mirror? So these are very, very important questions. And to answer these questions, we have this particular lecture. So we are going to use a tool called ray diagrams to answer these questions. I hope you are excited to know about our activity and the corresponding ray diagrams. But now, before we do that, we have a routine if you remember. Every lecture, we talk about a famous saying. It could be famous by itself, or it could be given by a person who was very famous or who is very famous still. So our saying for today, please listen carefully. A person who never made a mistake never tried anything new. Once again, Listen carefully. A person who never made a mistake never tried anything new. So that's a very, very, very wonderful saying. It has a lot of meaning. I want you to interpret it yourself. At the end of the lecture, I will talk about it just for a couple of minutes. Before we move on, I want you to know who gave this one. It was given by none other than Albert Einstein. You know about Einstein, right? So I'll give you few details about Einstein. Have them do a little bit of research by yourself in the internet. Albert Einstein, he was a very famous physicist and he's also a role model for many, many people. He was a pacifist too. He loved peace. But let's talk about his physics theories. So there are three of his theories which were very, very famous. One of them which gave him the Nobel Prize. The other one made him super famous. Other one, we know the equation, we have heard a lot, but we never thought much more about it. Let's talk about those three theories. The one that gave him the Nobel Prize was the photoelectric effect. So let's say the first one is the photoelectric effect. It was the founding steps for quantum mechanics actually. The second one, which made him very famous at a very early time, was the theory of relativity. So you heard about it, right? And the third one, which we all know, it's the equation E is equal to mc square. It's the relation between energy and mass energy equivalence relation. So these three theories are very famous. And not only that, in his close circle of friends, Einstein was famous for one more thing. He was a wonderful musician. He used to entertain his friends with his guitar. And based on that saying that we just heard, you can also say that he's a philosopher too. Okay, so all I request you guys is to have your own interpretation, but make sure it has a positive meaning in it. Don't go towards the negative side unnecessarily. Okay, so at the end of the lecture, I'll spend a couple of minutes to explain it in my own words or to give my own interpretation. Now, let's go ahead and start with our main lecture. This is the plan for our lecture. So we have three parts in it. The first one is understanding the purpose of ray diagrams. So why do we need to follow this procedure? That's the first thing. Then to have the ability to do it yourself, you need to have the prerequisites. Not only just for that, in order to understand what I am going to explain to you, you need to know something beforehand. So those are these prerequisites. And last one is your part. That means what you need to practice, how you need to practice. That I'll show you along with me. First look at the initial one. What's the purpose? This slide points out to the reason why these ray diagrams are very important. You can already see the ray diagrams. You have the rays from the sun hitting the mirror, and then the mirror is placed at a particular orientation that all the rays from all the mirrors are actually hitting the boat over here. It could be a ship, it could be a boat. This particular concept was thought to be done or performed by Archimedes in order to evade from Roman ships. So these are the Roman ships supposedly, and these are the mirrors by the Greeks. So let's try to understand what these ray diagrams are. So essentially the ray from the sun hits the mirror, and we need to know the physical phenomenon or the physical law that guides us in understanding which direction this particular ray travels through. Why is it traveling only in this direction? Why not in other direction? For that, we can draw a small thing over here. I'm going to draw a line with a red color ink. So this is the mirror. I want to draw a normal to the mirror at that particular point. As you can see, that's the normal to the mirror. I'll do something similar over here. The normal to the mirror. It's a little off, but it's alright. You get the sense of what I'm trying to do over here. And that's the third normal. If you observe, this is the first set of rays. If you call this the incident angle, this will be the reflected angle by the mirror. So as you can see, it has the same angle on both sides. The same thing applies over here and the same thing applies over here. So angle of incidence at the mirror is equal to the angle of reflection. So this is nothing but the Fermat's principle that we have been learning from 7th class. So in order to know, or in order to use the ray diagrams, we need to do two things. We need to know how to use the geometry, that means the scale, compass, and also the physical law over here. So here the straight lines is what we need to draw, and the physical law is the Fermat's principle of angle I is equal to angle R. As simple as that. Let's look at the next slide. Now this is a pinhole camera. The rays from the top of the tree is traveling in a straight path. It's entering into the hole and it's hitting the screen. This last one, the square that you are seeing over here, that's the screen of that pinhole camera. Similarly, another ray is projected over here from the base of the tree and it's actually traveling towards the top of the screen. So those are the two rays. You just have two rays. I mean, you can have a bunch of rays, but one from the top and another from the bottom is enough. And the reason why you are seeing an inverted image is simple. Rays from the objects in a single material, all this is air. So all the rays are traveling in a straight path. The physical law over here is straight path. Light travels in a straight path when there is no other material in between. And that's the ray diagram. With the ray diagram, we were able to understand why you see inverted images in a pinhole camera. Let's look at another example. That's the human eye. So you can see over here, these two are a couple of incident rays. They are parallel to each other, which suggests that the object is very far from the eye. So all the rays very far from the eye travel in straight paths, and when they enter into the cornea, this region is the cornea, the white color portion of your eye, the front portion, and it has a lot of liquid, a dense liquid, and because of that liquid, you have some convergence over here, okay? And then because of the crystalline lens, this is the crystalline lens inside our eye, and these are the ciliary muscles. We will learn about this in detail in the 5th chapter. Now, because there are two convergences over here, one is because of the cornea, and the second one is because of the crystalline lens. So rays converge, and ultimately the rays are actually pointed over here on the retina. This area is the retina, and all the information will be taken to the brain from the optic nerve. This region is called the optic nerve. So don't worry about various parts of the eye. That's not the lecture right now. What you need to see here is the physics. So the physics is simple. Here, as you can see, the cornea and the crystalline lens, what are they doing? They're actually converging those parallel rays. They're bringing those rays closer. That's the physics part. So in order to draw ray diagrams, I told you already, it's just two things. One is understand the physics and represent that physics using geometry with straight lines, angle lines, protractors and all that. So you learned about periscope already. I mean, your 7th or 8th class. I think it's the 7th class. So in that periscope, if you observe carefully, the two mirror arrangements over here, and these are all the rays, the yellow colored region is the light rays. We'll talk about that a little later. Let's observe these two mirrors. I want to draw horizontals at those locations. I'll draw a horizontal here. I'll draw another horizontal over here. If you observe carefully, the angle made by the bottom mirror with respect to the horizontal and the angle made by the top mirror with respect to the horizontal is the same. And in fact, it's 45 degrees. Only then you can actually have rays that are coming horizontal enter into your eye perfectly. So equal angles is a crucial part for a periscope. So that's the physics part. And what is the rest? As you can see, any ray coming over here, it's traveling perpendicularly down. Why is it traveling perpendicularly down? I can draw another normal to this. This is the mirror A, and I'm drawing a normal over here. And as you can see, angle of incidence, this is the incident ray, and this is the reflected ray from the first mirror. They're making the same angle. So the two physics parts we have here is Fermat's principle again. Angle of incidence is equal to angle of reflection. And the logic tells us based on this theorem that the two mirrors should have the same angle with respect to the horizontal. Same thing goes over here. Let me put another normal to the bottom mirror. So that's the normal, and clearly this is the angle. That's the angle of incidence, and this we can say angle of reflection. So as you can see, they're making the same angle again. And ultimately this particular ray travels 90 degrees and again another 90 and finally enters into the human eye. So that's what's happening over here. So you can see how powerful these ray diagrams are. With the help of these ray diagrams, you can imagine everything beforehand, and that will help you create all these optical instruments. The optical instruments we saw over here is the human eye. Of course, we can't create it. And the pinhole camera. In order to make a pinhole camera, first you need to draw the ray diagram over there. And you already saw the Archimedes thing. We can definitely try this out. All we need is plane mirrors or concave mirrors for this. Okay, let's see our last example. I have a solar cooker, couple of solar cookers over here. You can see, I want to describe what we have over here. So that's a concave mirror, a huge concave mirror. And I have a cooker over here and same thing over here. Based on this orientation, it's either sunrise or sun setting time. And the second cooker, it's more towards the afternoon kind of, somewhere between 11 to 2 o'clock, 11 to 3 o'clock time in the afternoon. And I have the cooker over here, and that's the concave panel. You can see the way they created it, looks like multiple pieces are attached to each other. Now, what's happening over here? Rays from the sun are always parallel to each other. The reason is sun is very far from Earth, so we can expect that any distant object gives us parallel rays. So all those parallel rays hit on this one. So I want to show you a couple of those rays, just an imagination of course. Let's say that's one ray. I'll use the red. That's the second ray. I want to draw again one more. So imagine these two rays are from the sun. Of course, there are a lot more rays. And when they hit the concave mirror, they pass to the focal point of that mirror. So that's, as you can see, these two are the incident rays and this is the reflected. That's an incident ray. Similarly, this is an incident ray and these two are the reflected rays from the mirror. Now, as you can see, the two reflected rays are converging at this particular point. That's the focal point of this entire concave mirror. And at that focal point, if you place your cooker or the vessel which you want to make it hot, that particular vessel becomes very, very hot because all that energy is converging at this point. Now, you can clearly see everything happened because we know the ray diagrams. We know that the parallel rays from the sun converge at the focal point, and as simple as that, we are placing a vessel at that focal point. So try to think about all these examples, and I just gave very few examples over here. You can have a bunch of optical instruments. It could be the projectors that are available in the movie theaters. It could be microscopes, telescopes, whatnot. Every optical instrument, before they create it, before they manufacture it, they definitely test out all these ray diagrams. The next few minutes of content that we are going to discuss is extremely important for us to understand the rest of the lecture. The purpose of this lecture is to understand ray diagrams when an object is moved in front of a concave mirror, and that was our lab activity. And in order for you to understand that, the next slides are extremely crucial. So I hope you have already gone through them from the slides and the content provided to you by your teacher. But anyway, I'm revising them once again here so that we all could go with the same pace. So follow these next slides extremely carefully. So the first slide
is ray 1. So please observe, we'll be using R1 for this instead of writing ray 1 in the future slides when we start with the main work. Now, this is a concave mirror and you have the paint on the back side of the concave mirror. So the front side is the mirror surface. Ray 1 is parallel to the principal axis. The line joining P and C is the principal axis and ray 1 is exactly parallel to the principal axis and it is incident on the concave mirror, right? So what's happening after that? The blue line is the reflected ray. Whatever the incident ray comes and touches the concave mirror reflects in this direction. And if you observe carefully, it's actually passing through the focal point. Now let's frame I would not say it's a rule, but a statement as such. A statement for R1 or ray 1. Any ray parallel to the principal axis reflects while passing through the focal point of the mirror. Once again, any ray parallel to the principal axis reflects while passing through the focal point of the concave mirror. It's very simple. A ray parallel to the principal axis will pass through the focal point of the concave mirror. That's it. Parallel passes through focal point. These are the keywords. Now, you don't have to actually by heart this. It's logical and it's common sense because if you see the normal, now what we have here is a line joining between the center of curvature and the incident point. This is the incident point of ray 1. If you join a line, this is the normal to that particular curvature at that point. Now, if you see carefully, whatever angle ray 1 is making with the normal, the same angle the reflected ray is also making with the normal. It's the Fermat's principle of angle I is equal to angle R. Angle of incidence is equal to angle of reflection. So, if it is 40-degree angle here, it should be a 40-degree angle here. So, this is not like a rule or something, it naturally happens. Any ray parallel to the principal axis will pass through the focal point of that mirror. Okay, so that's ray 1 or representative ray 1. Now we have moved to representative ray 2, the second representative ray 2, and focus only on the green and the blue lines. The green line is the incident ray and the blue line is the reflected ray. So what's happening, please observe. It's actually the reverse of ray 1. Ray 1 we had a ray parallel to the principal axis and it passed through the focal point. Now if you observe carefully, ray 2 is projected in such a way that it passes through the focal point of the mirror and as soon as it incidents on the mirror, it's becoming parallel to the principal axis, right? It's the reverse of the first case. Let's frame a sentence for this. Any ray passing through the focal point will reflect parallel to the principal axis. Once again, any ray passing through the focal point will reflect parallel to the principal axis. Again, this is not a rule. It's based on geometry and Fermat's principle. Now I have the normal line, the black dotted line again over here between the incident point and center of curvature. And again you can see the angle between the incident ray, the green one and the black one. And the angle between the reflected ray, the blue one and the black one. The incident angle and the reflected angle are again the same. So it's again Fermat's principle and geometry. So that's with ray 1 and ray 2. We'll get to ray 3 a little while later. But help me with this. Imagine you have a plane mirror. And this is the normal to that plane mirror, right? When a ray is incident on the plane mirror, along the direction of the normal, which direction would it go? Think about it. This is the normal line and incident ray is also traveling along the normal line and hits the mirror. So it travels right back in the same direction. So doesn't matter if it's a plane mirror or a concave mirror, any ray traveling in the normal direction will go back in the same path. So that is what is this representative ray 3. Now you have the center of curvature and let's say this is the incident point. Now a ray is traveling along the C and it hits the concave mirror and it travels right back in the same direction. So what is representative ray 3? It's the straightforward ray where the light ray travels in the 0 degree direction. That means along the normal direction. So let's put it in a statement once again. Any ray passing through the center of curvature will reflect back in the same direction. Any ray passing through the center of curvature will reflect back in the same direction. So if you understand the Fermat's principle from your 7th and 8th class, these are just extensions of that for a curved surface. We learned about plane surface over there, and here it's curved surface. That's the slightest difference. Let's go with the ray 4 right now. Now, green one is the incident ray. It's traveling and it is striking the pole of the mirror. And observe carefully, this is the reflected ray that's traveling in the other direction. Now, in this particular case, at that location, at the location of the pole, the normal line is the principal axis. This is the C, center of curvature, and P is the point. Any line passing through the center of curvature is the normal. So here, a line joining P and C is the normal. So that's the normal. And if you observe carefully, whatever angle the incident ray is making, the green one is making, the same angle the blue colored ray will make. Representative ray 4, it's not very helpful for us to draw the ray diagrams. We can definitely use it. I mean, we'll get good results. But this is more widely used during derivations. When we derive the formulas, this representative ray 4 will be extremely useful for us. So with this knowledge of the 4 representative rays, we can easily understand how all those images were formed in our lab activity. Why we saw varying sizes, why we saw inverted images, why we saw real and virtual images. All those answers can be obtained using these 4 representative rays.
This is the second prerequisite. We constructed this table from the lab activity. This was the conclusion of that lab activity, where object distances were placed at beyond C, at C, between F and C, at F, and between P and F. For each and every position of the object, the image position has changed. The second column corresponds to that, and also the size of the image has also changed. Sometimes it was diminished, sometimes it was same size. We saw enlarged images, multiple enlarged. And we did not see just inverted images, we saw some erect images also. And also some of the images we call them virtual when we have seen them inside the mirror, and some of them we call them as real images. And at F, when object was placed at focal point, we had this mystery. I mean, we left them blank. So all these were observed. I mean, while performing the experiment, we observed it, we tried to understand it. But the reasons behind those observations was not analyzed during that time. And now this ray diagram activity that we are going to do for the next few minutes will help us understand the reason behind each and every of these observations. And we are going to start with beyond C, then we'll go to at C, then between F and C, at F, and finally the object between P and F. So let's go ahead and start with constructing the ray diagram for beyond C. Let's look at the tools that we have for this part. So I have a concave mirror over here. So the trick for getting good results is not to randomly draw an arc using your compass with a pencil and all that. The trick is to draw a very large arc. So don't take the diameter or the radius to be small. Take a large diameter and draw a small arc around it. The reason for doing this is all the ray diagrams or all the derivations that are given in your textbook, they're applicable for thin lenses or thin mirrors. And when you use a radius of very small, like 5 centimeters or 8 centimeters, that means that they are not thin lenses, but they are very thick lenses. And all the rules or all the things that you have observed will not be applicable for such mirrors. So in order to get results, you have to use radius very high. Maybe 15 centimeters as radius would be a good start. So I want you to practice with 15 or 20 centimeters. And anyway, you're not going to draw the entire circle. You'll be drawing only a small portion of a circle. Now, so that's my concave mirror because I've painted the back side with those lines and the front side is the mirror side. Now, if you observe, this point is the pole and I have the center of curvature over here. That's a line joining both P and C. So what should that line be called? Yes, it's principal axis. Okay, it's not principal, it's principal axis. Now you have the principal axis and I have a point called focal point, F. So my question is, where should we place F? Is it closer to P? Is it close to C? Or should it be in between P and C? What is the best choice? So if you remember from our previous discussions, we already had this, right? So we have the formula. There are two ways of going about this formula. So let's check that out. So you can use the formula as R, that's the radius of curvature, which is equal to 2 times focal length, or of course F is equal to R divided by 2. Now, if the radius of curvature, that means the distance between P and C is 10 centimeters, then focal point should obviously be at the center, that means at 5 centimeters. Let's check first the distance between them. So I'm placing the scale, I'm using the scale as a tool over here. So when you're drawing it with your material, you need to have a scale around. Now I'm placing the 0 centimeters at P because all the distances should be measured from the pole. And as I can see over here, if you check carefully, this particular point is at 9 centimeters. So radius of curvature is 9. What is 9 divided by 2? Yes, it's 4.5 centimeters. And that's where I have the focal point. It's at 4.5 centimeters. Now, I don't need the scale anymore for now. So I'm just getting rid of the scale. Now, what are the other tools I have to draw these ray diagrams? One is R1, that's the representative ray 1. If you remember, it is the ray which is parallel to the principal axis. R2, representative ray 2, it is the ray that passes through the focal point and it hits the concave mirror or the convex mirror. And then I have a candle over here. We'll talk about this other candle which is inverted. We'll talk about that a little later. To avoid any confusion, what I'm going to do is I'll be using green lines for incident rays and blue lines for reflected rays. The one that's hitting, the travels to hit the mirror will be in green. And the one that rebounds or comes away from or goes away from the mirror will be blue. So let's go ahead and do that. First, I need to place the candle at an appropriate location. And based on our discussion already, we know that the candle will be placed beyond the center of curvature. So that's the first thing that we are investigating. So I'm picking a representative ray for ray 1. And as you know, we'll have a parallel line to the principal axis. But I want you to think about something else. All the rays are coming from the object. So object is releasing those rays. And we are using only these 3 representative rays. R1, R2 and R3. And also we are actually picking the tip of this flame, the flame tip, as the one that is actually emanating all these rays. So let's start with the tip, and from there I'm drawing a line parallel to the principal axis, and let's think that it's hitting the mirror at that particular location. Since they're traveling towards the mirror, I'm going to place an arrow mark something like this, and I'll move this R1 alphabets over here to point out that this is the representative ray 1. Now let's go ahead and use a blue line to see the reflection. Now, we already know any ray parallel to the principal axis will travel through the focal point. Any ray parallel to the principal axis will travel through the focal point, and that's the reason I'm drawing a line so that it is passing through the focal point. Since this is a reflected ray, I'm putting arrow marks away from the mirror, right? Now let's go ahead and pick R2. R2 is the second line. Again, I'm picking the tip of the flame, and from there I'm going to have R2. The second representative ray, if you remember still, it is the ray that passes through the focal point and incidents on the concave mirror. So it's passing through the focal point, and since it's traveling towards a mirror, my arrow direction will be towards, and this is R2. Now try to remember the representative ray 2 reflection. Any ray passing through the focal point and incident on a concave mirror will become parallel to the principal axis, or will reflect parallel to the principal axis. So I'm drawing the second reflection from the incident point and I'm making a parallel line. So that's the second reflected ray, and since it's also traveling away, it's a reflection. So that's why the arrow mark is over there. Now observe this point, this location where the two reflected rays are meeting. This particular point has emerged because of the rays coming from the tip. So that's the reason I have this inverted candle over here, and if you observe carefully, it exactly matches. I don't have to resize it, and since it's emerging from the tip, this point should be corresponding to the tip of the candle, but here this is the image, whereas this is the object. So that's the entire ray diagram, and it's very, very simple. All we did was we picked two representative rays out of the four available, but as we already spoke, the fourth one we use it very rarely. Now R1 and R2, the reflected rays meet at a point, and that point is the tip of the candle, so I have an inverted candle over there. Now let's think about all the properties over here. Before we categorically show it on the screen, first tell me the size of the object. Is it big, or do you think image is big? As you can see, image is definitely smaller, so that's an important point. Now, when object is beyond C, where is the image? As you can see, the image is found between F and C. Now, is it erect or is it inverted? Is the image erect or inverted? And you can clearly observe it's below the principal axis, so we should call it an inverted image. And finally, should we call this image a real image or a virtual image? During the lab activity, we just kind of as a rule we said that any image that forms on a screen on the paper is real. Anything that we see inside the mirror is virtual. We kind of made it a rule. It's not a rule, of course. We made it a rule and we started remembering it like that. But now I want you to think about something else. I have a question for you. This is the first reflected ray from R1 and this is the second reflected ray from R2. If you observe those two sketches, are they really meeting at this point or is it our imagination? You might be wondering it's our imagination because you were drawing the whole sketch. Now think of it like this. It's a candle. Rays really emerge from the tip. Definitely rays come out of the candle. These two are real rays. So the two reflections are real reflected rays. Since they are meeting at a point really, so that's the reason we call this image a real image. Very simple. Anything that can be touched is real. So this particular image that we saw on a paper, we can definitely touch it. We can touch it. Of course, we will not feel it hot, but we can still touch that flame. So that's the reason it's called a real image. Now, let's summarize it with few sketches. It's a different sketch, but still the same result. Object is beyond C and the image position is between F and C. And what about the size of the image? It has diminished. It's smaller than the object. We use the word diminished. So that's what I have over here. Now, is it erect or is it inverted? If it is similar to the object's orientation, that means flame upwards, then we call it an erect image. Since it is reverse, as you can see, it's in the reverse position, we call it inverted. Now the last one, we had a deep discussion about this. Do we call it a real image or a virtual image? My explanation was, since reflected rays are really meeting at a point, we call it a real image. Now let's move on to the next one, where we place object on the center of curvature.